everybody. This is Dr. Keith Schubert. I'm going to attempt to redo my blood pressure stuff because the other ones I'm having great trouble uploading. I'm going to try to hit some of the key features on this one on how things are measured. So the book mentions that there's 3 different methods for doing this, and there's the pictures they draw I don't think really kind of do justice to what really is happening here. So I'm going to try to get into this. 2 of them are based on the same technique that's in, right? So there's what's called a sphygmomanometer. They give you a lot of the history in the book. It's kind of a fun word to say, actually. But a sphygmomanometer is basically that cuff they put on your arm. And there's a bulb, and you pump it up with air. Originally it was started with water, and there's also a pressure meter on it. So the manometer part is actually the measurement. The sphygmo is actually talking about that basically bladder that's filled with a fluid to compress on your arm. So that compression one is used. You inflate it past the point of when blood no longer flows, and you can. I wouldn't say it's super easy. I've actually never done it, but I know the theory behind it. If you've got a cross section, so imagine you've got somebody's arm. I don't claim to be an artist, but if you've got, so here's the bone in the center, and you've got blood vessels that are in here. And these blood vessels, I'll do a kind of a blown up view here, right? Blood is flowing through this. And as you constrict on the person's arm with the cuff, and it's pressuring in on all sides, it's going to squeeze the blood vessel. And as you keep adding pressure, it squeezes and squeezes, and eventually it seals it up so that no blood flows. As it starts squeezing it, the blood has to flow a little faster to get through there, and so it makes that kind of like a characteristic noise, right? They call it sputtering noise, or however you want to say it. As it's flowing through, though, they can hear. So before it starts compressing anything, there's no real sound to it. As it starts compressing, sound starts. You get all the way up. Once it fully compresses it, there's no longer any fluid flow, so there's nothing making sound. So at that point, the sound shuts off. And so that's how they can tell that they're above it. So they pump and pump and pump until the blood no longer flows. So technically speaking, you can do this technique on the upside or on the downside. Now, that being said, the question is, do they give the same number? And the answer is no, they don't. So it turns out that it's less accurate when you're inflating. So this is why everybody always does the measurement on the deflation part. Some of this kind of makes sense. Once it's already flowing, it's going to tend to cause you to get a different pressure reading. So when we want to get the accurate measure of the static when it first opens up, so you don't want any flow in there, creating pressure differentials inside the blood vessel because of the flow of the fluid. So when fluid flows through there, it'll cause a pressure difference as it's flowing, and that pressure difference will actually mess up your measurement. When it's not flowing already, everything's much better. So a lot of studies have been done, and they found out that this is indeed the truth. It just makes sense, particularly for those of you who have had a mechanical engineering background. You can think about fluid flow through pipes, and works exactly the same. So, in any case, that gives you the idea of squeezing them off. So we're going to measure them when it comes down. You want to put the cuff about the same level as the heart. This is kind of important because you don't want a pressure differential caused by gravity to handle the change what's going on here. And then what they're going to do, so they're going to so this is time, and you measure pressure. And the pressure is going to come down, and somewhere around here, you're going to see the actual pressure wave. The blood pressure wave is going to look, depending on where they catch it, some type of a peaky wave like that going through. That's the actual pressure. Now, as this comes down, once the pressure inside the blood is higher than the pressure of the cuff, it'll open that valve up. and then fluid will start flowing. So you're going to hear the sputter noise. Now, the reality is this wave is much, much faster than this decay is. So it sounds pretty much continuous when it's going through once it's opened it up. And at a certain point, it'll hit the bottom. And below that, it's not enough to cause any compression, so the noise goes away. So if you're doing it by the oscillatory technique, right? Right, so osculatory technique. It's from the Latin word to listen, right? So this is kind of the listening technique. They put the listening device here just below the cuff, and they just listen to those sounds when it comes through. And all you're doing is picking, you get the systolic and the diastolic pressure. And that's why systolic is always the bigger number, because it's when it starts and when it ends, so it has to be bigger because it's constantly decreasing cuff. That's what doctors tend to do in the market. It's been, in the doctor's office. There are some that will use the next technique, but most of them tend to do this. It's an extremely accurate technique if you've got somebody who can listen correctly to sounds. It can be fooled a little bit from what I'm told on this. I'm not going to say I'm an expert on these, but evidently when you get high blood pressure, and this kind of makes a little sense, the sounds can be harder to distinguish. So getting the exact pressure range for somebody who has hypertension is going to be a more difficult maneuver. Now, the second technique is based off oscillatory, right? Meaning to oscillate. So it's called oscilliometry. Metry, right? So, but think oscillate, right? And the idea is these waves on here, they're not this big. So when they show this in the book for the oscilliometry, they show the wave going through, and the wave is huge. It's like the full size of the wave. Totally not true. When you actually look, that is the size of the actual wave. But when it gets onto this, you'll see some noise variations as the pressure's coming down. And once it gets into this range, you'll see these little kind of pulses, which are that wave going through. And what you're actually seeing here, and then they'll die off as they come down, but there's always some noise going down. But right in the range where your heartbeat is, they're bigger. Okay, so that bigger wave that's in here, you can pick these up with a very, very sensitive pressure meter. A human's not going to do it eyeballing it, but I can put a machine that's going to oscillate or measure those oscillations very, very quickly and very accurately to find out what these look like. And then to get the actual waveform, what you do for oscilliometry is you take this, the main wave that it's imposed on is a pretty slow moving one. So if I hit it with a high pass filter, it'll basically knock this baseline out. Typically somewhere around half a hertz is good for this. So a high pass filter with a cutoff around half a hertz, and what will happen is this whole baseline will go away, and then you just amplify these waves up. And what you'll see in its place is now it can go above and below. You'll see little tiny waves coming in, and it'll start growing. And you'll see these, the classic beat waves, right? Like those kind of two pulse. And it's got an envelope. The envelope you don't actually see, but the envelope kind of looks like that. And it does indeed go past a little bit, not quite that far. So, the peak hits a little earlier on the positive side, a little later on the negative, and these go all the way down. Right. So when you're going through these, right, the very first time where this kind of sharp change in what's happening here, you'll see an increase zone. And that, when you see that kind of upturn, right, that is when you know that your systolic number has hit. On the other side, you can see the kind of downturn, and that tells you where diastolic is. Now, you can also get where the maximum wave height hits. Right? That is where the median value is. So the median aortic pressure, or MAP, is located here. Now, when you look at what they're showing, when they draw it in the book, it makes it look like the figure like is imposed on top of this. Like I look for the biggest wave, and you are looking for the biggest one of these, but they draw the peak way up here and they say that's MAP, and that's not true. Where that biggest wave hits here, time-wise, I can look back here and that gives me what the pressure is. I can find this little corner here and that tells me where that happened time-wise. I can look at the original one where I didn't remove the baseline, which gives me my height, and I can look back and measure the pressures. So pressure systolic, pressure of the median, and pressure diastolic. I do by locating these features inside the graph. So the biggest height-wise, after you've hit it with a high-pass filter, the biggest height-wise one, charting that point back up gives me what the median aortic pressure is. So if you look at the picture in the book, you'll be confused as heck. So I hope this helps you understand what's happening. So, this is what you measured. And then you go through a high pass filter. You get this, find the peak, right? You get the contour of these waves. They're really pretty tight together. There's not very big gaps. If you'd actually draw it, it'd look like, right? But if you zoom in on them, they really do have the classic lub-dub type shape, right? The double peaked. And you find where it's biggest, and that is where MAP is, and you look for those little corner breaks, and that gives you these two. So hopefully that helps you understand better how oscilliometry works. That allows you to design a machine to do those. The other way is pretty straightforward. It's used in surgeries. So imagine I was having some type of a heart surgery, or please don't imagine that. I would rather not. If I was in that situation, right, and they needed to do it, they could actually insert a catheter into one of my blood vessels, and they could have a transducer in it, and they could just directly measure the blood pressure. That's going to be extremely accurate. It's highly invasive. So these two are the non-invasive ways. There are other ways. These are the two really accurate non-invasive ways. The invasive way inside of a surgical hospital is going to be to actually, right, stick a probe that's going to allow a transducer to directly measure the pressure in my blood. So that tells you basically the way that each of these devices actually works, right? And since the other one's just directly in there, I can measure the systolic and the diastolic and the median. Now, on the oscillatory, they really don't have a good way to get the median, so they will often, for that one, for the oscillatory, so this one gives you the systolic, the diastolic, and the median. Oscillatory gives you systolic and diastolic, but it does a really good job at them. And you can approximate the median. So the median pressure, median aortic pressure is about 1/3 the systolic plus 2/3 the diastolic. This approximation works well for most people. It's kind of aimed towards adults and basically reasonably fit adults and stuff like that. So as you go to high blood pressure or other types of things, it gets worse and worse. But it's kind of a good general guideline. It just turns out diastolic should have a little more weight than 50-50. So you can get a good approximation from the oscillatory. Like I said, all the pressures can be exactly measured when you got a transducer, or up to the transducer's accuracy. Standards say that transducer has to be less than 1 millimeter of mercury. So, when they give you the numbers, your blood pressure is whatever, 110 over 70 or something, right? Each of those, that's in millimeters. So that's when we're talking about this, for the doctors measuring in a surgery, their accuracy at worst is, would be that 110 plus or minus 1. And the 70 plus or minus 1. Now, your actual blood pressures will be much lower because you've been anesthetized if you're going through the surgery, and anesthesia lowers your blood pressure. But that's a whole nother discussion that's not directly germane to our situation. So I hope this helps. The rest of the book stuff is awesome. The history stuff in there is spot on. Descriptions, their pictures are much better than mine. It really bugged me. The big thing that gets me is the oscilliometry picture and description is just, it's bad. So, hopefully that clears it up. Anyway, have a good day. Hope everybody's staying healthy.